All right. Welcome everyone back to another Astronomy on Tap, our ninth one so far, Deep Space Virtual 9. Glad to have you with us. My name is Michael Roderick, and together with Arvind Gupta, Brianna Twatsky, and Jacob Lund, we run Astronomy on Tap State College. So if this is your first time here, the way this works is we have two talks for you, talking about Dyson spheres and dust. We're going to start off with a quick astronomy cocktail with Jacob. Oh, excuse me. With Jacob, I've been drinking too much of my drink already. With Jacob, then we're going to have our first talk of the night, Dyson Spheres by Macy Huston, followed by trivia with Arvind, astronomy in the news with Brianna, and then back to our second talk of the night, talking about dust with Alex. So I'm going to go ahead and pass this over to Jacob, who can get us started with our drink. Take it away, Jacob.
Awesome. Okay. So hopefully you saw the ingredients there and were able to get them. I'm told that aloe vera juice is maybe not the easiest ingredient to find, but if you did, congrats, you get to make this with us. I think also in a few places I had put that the beer of choice was a citrus IPA. I've actually just taken a shock top, which is just kind of an orangey Belgian white. So a little bit of a change. I apologize for that. It's been a snowy season, and so I haven't been able to get as many ingredients as I would have liked for some of these tests. But tonight we're going to be making our drink, and it's pretty easy. So it's going to take some gin, some vermouth, this beer, aloe vera juice, grapefruit juice, and orange juice. And if you're not big on grapefruit juice, you can kind of switch the grapefruit and orange in and out, or kind of omit it altogether and just do double of the orange, and then it's just a little more orangey. So that's also an option. So we're going to start with the gin. And as I mentioned, this is kind of an easy recipe or cocktail. Kind of all the amounts are the same. We're going to do about 2/3 of an ounce, or if you want a slightly more or larger volume, you can do a full ounce. I'm going to attempt to do 2/3 of an ounce here of each of these. Well, that one was a little larger. So I'm just playing it kind of by eye. So up to you. Kind of keep the amounts roughly the same. And I'm basically out of vermouth, so I think I'll have just enough for the rest of it, and that's just about 2/3. Perfect. And then we're going to do our aloe vera. We're going to save the beer for last because that one's actually a larger amount. Again, about 2/3. And we're also going to be doing 2/3 of grapefruit and orange juice. But as I mentioned before, you can kind of mix and match those. So you might be wondering why this is an astronomy themed drink. And the answer is this one's a bit of a stretch or a contrived astronomy themed drink. I have found a cocktail, again, 2/3 ounces here. I found a cocktail called the Reuben, and we're adding some aloe vera to it. And so we're calling this drink the aloe vera Reuben. And if you're not familiar with famous people in astronomy, Vera Rubin was an astronomer in around the 70s, and she was very famous for discovering dark matter. So dark matter had been kind of theorized for a while, but she was the one to kind of first actually discover it. And we'll talk about that in just a second. But we've gotten to the beer, and we're going to add about 6 ounces or so, or I'm going to basically mostly fill this glass. You don't want to do the whole beer, so you will have some beer left over, but about 6 ounces or so. Again, I'm just going to kind of eyeball it, fill it to the top, and I'm going to put some ice cubes in here as well. Just a second as I step out of frame, grab some fresh cold ice cubes and put them in. But how she discovered dark matter is actually kind of interesting. So if you think about the solar system and rotation rates of the solar system, we know that like Jupiter and Saturn, the farther out planets, take longer to orbit the sun. But what Vera Rubin found was that in a galaxy, a lot of the stars orbiting the galaxy at large distances were orbiting at the same rate that some of the inner stars were orbiting. And so this was very intriguing. And bottom line is you can explain it with a little dark matter halo. And so as I finish off this drink, I'm going to kind of stir it up, kind of mix it well. And as you stir it, you can kind of think about rotation rates of galaxies, thinking about kind of spiral and elliptical galaxies, and thinking about how it's kind of strange that for these galaxies, because of these dark matter halos, the outer edges of these galaxies actually rotate just about as flat or as fast as the innermost regions of the galaxy. So this is our Aloe, Vera, Rubin Astronomy on Tap cocktail. Hope you enjoyed those Vera Rubin fun facts. Cheers.
Cheers. How long have you been waiting to say that? The Vera Rubin fun facts.
A while, I guess.
Very nice. All right. Well, thank you, Jacob, for making our drink. So now that you've all got something to drink, we are going to go ahead and get started on to our first talk of the night. So we have a fellow graduate student at Penn State, Macy Huston. She's going to be telling us all about Dyson spheres and, of course, how totally we've detected those alien signatures all over our galaxy. All right. Take it away, Macy.
Am I good?
Yep, looks good.
Okay. Yeah, so spoiler alert, I won't be announcing that we've found aliens. Sorry, guys. But I am going to talk about some ideas about ways that we might be able to find aliens someday, and also some reasons why popular sci-fi is wrong. So just kind of to start off with, I wanted to mention kind of the origin of the idea of a Dyson sphere. This comes from an old sci-fi book from the 1930s. It's called Star Maker by Olaf Stapledon. And there's, it's basically the story of a human man whose like consciousness gets separated from his body and just goes through this amazing adventure through the universe. I haven't actually read the whole thing yet, but this specific part I wanted to talk about is they say every solar system is surrounded by a gauze of light traps which focus the escaping solar energy for intelligent use so that the whole galaxy is dimmed. So this is kind of the basic idea of a Dyson sphere, is that you've got a star emitting a large amount of energy. You can build up technology around that to collect the energy and put it towards some sort of technological use. Before I get into Dyson's work, though, I want to just give a little bit of context for the early days of the search for extraterrestrial intelligence when this all got started. So it kind of got started off in academia in earnest in 1959 with this paper by Cocconi and Morrison. It was a really short paper, and it's just kind of a discussion about how extraterrestrial civilizations may attempt to contact us. So they figured messages would be sent in the form of electromagnetic waves because that's the fastest traveling thing we know of, traveling at the speed of light. And they figured it might be in the radio range, since radio is really good at transmitting even through things like gas and dust that get in the way. So they decided on the 21 centimeter neutral hydrogen line, just because neutral hydrogen is really ubiquitous, and no matter where you are in the galaxy, it's going to be something you see if you make astronomical observations. So they proposed a project to study the nearest star systems at this wavelength to see if anyone is trying to transmit a message to us. And I really like the last quote of this article. I think it's just really important to the philosophy of SETI. They said, "The probability of success is difficult to estimate, but if we never search, the chance of success is zero." So that brings us to Dyson in 1960. His proposal basically was that in addition to looking for extraterrestrial radio signals, we should also be looking at infrared light. So just kind of a summary and a quote from the paper. He said, "If extraterrestrial intelligent beings exist and have reached a high level of technical development, one byproduct of their energy metabolism is likely to be the large-scale conversion of starlight into far infrared radiation." So this idea basically is just that as civilizations grow, become more advanced, their technology advances, they're going to need large amounts of energy. And the largest energy producer by far in the solar system is the sun. So a logical step might be to try to harness that energy for whatever you're trying to do. And then when you take that energy out of the star and you use it for computation or some sort of technological use, you're going to turn it into heat, and it'll get re-radiated back out in the form of infrared light. So what he's proposing to look for is missing optical light from stars that has reappeared in the form of infrared light. Now, this paper was pretty controversial, and I'll read one of the quotes that kind of shows why. At one point in the paper, he said, "One should expect that within a few thousand years of entering the stage of industrial development, any intelligent species should be found occupying an artificial biosphere which completely surrounds its parent star." So this quote is interesting. It kind of makes a lot of logical leaps from what we were talking about before. Because, right, it seems like not that far of an extrapolation from where we're at that like maybe we'll want to get large amounts of energy. We might want to get them from the sun. But this occupying an artificial biosphere and that completely surrounding the parent star is a pretty strong statement that a lot of people disagreed with. So some of the objections were that a solid sphere would not be able to be constructed around a star in a way that is stable. So unfortunately, the structure in that Relics episode of Star Trek couldn't actually exist. One of the issues is that you want to keep your sphere centered around your central star, but there's not really any forces in place to do that. When you've got a big spherical shell, no matter where within it the star is, it's not going to enact any net gravitational or radiative force on the sphere. So if you get any type of disturbance to the sphere, it can just drift right into its star and get destroyed. There's also the maybe even bigger issue of mechanical instability. If you've got a really massive shell like this, a lot of times when we imagine them being out at the distance of Earth's orbit, so an astronomical unit. It's going to just be a huge sphere, and it's going to take so much material to make it that it's going to gravitationally collapse on itself. So some people have worked on this problem to try to come up with something that would be able to hold itself up. And basically they come up with that the very thinnest gold leaf might be able to work. But the problem with that is the whole point of a Dyson sphere is that you want to capture energy for technological use. And there's nothing useful about a giant sphere of gold leaf. If you want to put anything useful on the structure to capture energy and use it, it's going to have to be more massive, and it's just not going to be stable. There were also a lot of objections to Dyson's idea based on like sociological and political, economic concerns about such a giant project like this that would take generations and so much cooperation. I don't really think it's useful to speculate about alien sociology and politics, so I'm not going to get into that. But I will discuss Dyson's response to these issues. So Dyson clarified with regards to the instability of a solid sphere that he was actually imagining a loose collection or swarm of objects traveling on independent orbits around the star, rather than a solid spherical shell. So this picture here, I've just included an example of what one artist imagined that a Dyson swarm might look like. So in this scenario, you have all of these different objects, probably solar panels or whatever you want them to be. And they cover some large portion of the star, but not 100%. So when we look at these things, we might be able to detect dips in the starlight, or you can, if it's capturing a large amount of the star's light and using it, you will get detectable infrared emissions still, even if it's not 100% covering. Dyson's second argument was that these independent objects would not have to be a single coordinated effort. You wouldn't need global cooperation, multi-generational cooperation to send up each of these individual objects. So his idea was that different societies might just send up one single satellite at a time, and gradually it builds up toward covering a significant portion of the star. Dyson also clarified in this paper that the discovery of such an infrared object would not necessarily mean that we have found extraterrestrials. There are a lot of other things out there that can cause, weird dips in starlight, excess infrared radiation, things like that. So if we see a weird signal that looks like it could be this, we don't want to jump to conclusions, but it's a good source to follow up with some other types of studies, looking for things like radio emissions and lasers and stuff like that. So another kind of adjacent topic I want to mention here is the Kardashev scale. This was created by Nikolai Kardashev, and this paper was actually, seems to be the first mention of the term Dyson sphere. So he created a scale for types of civilizations. Type 1 is a planetary scale civilization. So it's a civilization that basically controls the entirety of its planet and its planet's energy. So us humans are not there yet. Someone extended the scale a little and said that we would be like 0.5. We're moving towards controlling a lot of the Earth. And then the second level here on the scale is a stellar level civilization, which would be something like a Dyson sphere, where you're capturing a significant amount of the star's light for your technological uses. And then type 3 here is a galactic scale civilization. This is actually what Olaf Stapledon was talking about in that book, Star Maker. So for example, his description of it was basically there was a Dyson sphere around every star, and something else about stars they didn't see fit for Dyson spheres. I don't know. It's kind of a weird book, but yeah, so Dyson spheres fit onto this stellar scale civilization, type 2. So I just want to talk a little bit more about Dyson's work on Dyson spheres. He went on to do some more specific math and try to prove to people that the idea of a swarm is realistic and physically possible. So he demonstrated that it's possible to build large rigid structures in space, and that you can build light rigid structures in space. And all I mean by light here is that the amount of material that you need to construct them is an amount of material that you can find in the planets in the solar system. You wouldn't need to go to other systems and grab planets to get the material to make this type of thing. And he also demonstrated that it's possible to deconstruct planets using energy scales that are possible to achieve in the solar system using the sun's energy. So I want to talk a little bit about this idea of transiting megastructures. So when you've got really large structures on the scale of your sun, so something like Dyson swarm, where you've got all of these little objects moving around the sun, they're blocking parts of its light at different times. So just kind of to explain a simple example of a transit observation. This is a method that people use to find planets a lot. So as a planet passes in front of its star, it's going to block a certain amount of the star's light. So you'll see the star get dimmer, flatten out as the planet moves across, and then it'll return back to its normal brightness, just in this very simple curve here. On the other hand, if you have something like a Dyson swarm or some sort of large structure constructed to collect stellar energy, for example, this weird shape I've shown up here, you're going to get some really strange light curves. Unlike this very simple planet light curve, you're going to get all of these crazy spikes, and it's going to look really weird. So just to kind of summarize the things that we look for if you're looking for Dyson spheres and megastructures, you can look for stars that are not as bright in the optical range as you would expect, because a certain amount of it is being captured. You can look for excess infrared emission that comes off of your technological devices after they have processed the energy they're using from the star. And you can also look for strange transit light curves for large and weird shaped objects passing in front of their star. I'm not really going to get too deep into the research looking for Dyson spheres in the past, because basically nothing too convincing has been found yet. I'm just going to kind of wrap up with a cautionary tale about the media running away with an incident of strange transit light curves. So this was in the news a lot a few years ago. You've probably all heard of it. Is Tabby star or Boyajian star, just named for Tabitha Boyajian, who was the astronomer who discovered these weird light curves. So in these images, I have shown some of the really irregular transits, really irregular depths, and really deep transits. So this is the kind of thing that could happen if you've got some really weird structure going on around your star. So one of the possible explanations for this could be a megastructure. The problem is that a lot of people in the media got very excited about that and started announcing that we had found aliens. We had found a partial Dyson sphere. There are alien megastructures that the Kepler telescope has found. And there was even at one point a professor who went on national news and was claiming, yes, we definitely found aliens. I don't think this person was an astronomer, maybe a biologist, but it was a pretty wild claim for them to make. And that was a whole big ordeal. But basically, people have studied it further, and what they think that they're seeing is a family of exocomet fragments, all of which are associated with a single previous breakup event. So there was some sort of collision of some objects out there that created a bunch of debris. And so you've got a bunch of weird shaped objects and a bunch of dust going on, just creating these weird signals as they orbit. And I think actually Alex is going to talk a bit more about that later when he talks about dust. So I just kind of conclude with, don't believe those clickbait stories about aliens. I know there's a lot of them about things like this, but you really just look at the peer-reviewed science, see what the people who actually work on this are saying. If you can see the papers that people are talking about in their news stories, go to the peer-reviewed journal article, you can read the abstract. If we don't say in the abstract that we found aliens, we probably didn't find aliens. And I know a lot of my family's on here. You can always talk to me when you see weird articles about aliens. I'll tell you if we actually just saw some weird transit signals or something. So yeah, study, we're looking for things, but we have not found aliens yet, unfortunately. That's all I got.
All right. Thank you, Macy. Kind of sad we haven't found aliens yet, but I'm sure we will soon.
Yeah.
All right. So if you do have any questions for our speaker, please do feel free to type them into the chat, and we can ask her while she's still here with us. I kind of have to mention this. You talked about stability of this Dyson sphere. There's a book written some time ago called Ring World, where they found a ring around a planet, and after the guy published it, a bunch of scientists came up and said, "Hey, that's totally gravitationally unstable. That would never work." So in the second book, he retconned it, and they engineered some stuff to make it all work. I thought it was kind of silly. All right, so we've got a question here in the chat. So in the transit curve of the megastructure with all sorts of spikes, several places where the curve goes to the continuum value, is there a way a transiting structure can do that? So I guess, can a transiting structure produce spikes and then go to a continuum value?
Right. So this plot is actually not just a simple light curve. It's about it's plotting the change in magnitude over time. So when you see it getting brighter, it's not actually getting above the base brightness, but it's just getting brighter than it was right before that. Does that make sense?
I understand it. All right. So we found Tabby Star, and that was actually, I think that was found through the Planet Hunters, right? That was a citizen science project which found the unusual
Yeah.
spikes. Have we found anything similar to Tabby Star in any other data?
That's a good question. Nothing has blown up like this. I'm sure there's been other weird things out there. I know one of the issues if you're looking for these sorts of things is that it's hard to, when we're looking at like Kepler data, there's just so much of it that people set up computer algorithms to sort through the data. So it's really easy, well, not easy, but it's possible to make an algorithm to look for things like planet transits because you know what that shape is going to be. But when you're looking for irregular transits, it's really hard to get a computer to do that. So you got to get people willing to look at them all by eye, and it's an intense process.
That is fair. All right, another question here from the chat. How would they actually get the energy from the structure to the planet or wherever they want it to be?
Yeah, that's a very legitimate question. I guess the way Dyson saw it, people would be living on these structures. So they would be kind of like mini planets, basically. So they would be where the energy is already. In other ways, I'm not an expert on energy transportation in that kind of way, so I can't really tell you.
If they are all reflective surfaces, could you beam it towards the surface of a planet or towards some like energy station and then transfer it from there to some other thing?
Seems possible, yeah.
It's like with aliens, you can just wave your hand and say, well, they're so advanced, I'm sure they find a way to do it.
Yeah.
So I guess kind of leaping off of that, we always talk about this, they would have this infrared excess, this kind of leakage of energy. Is there any way, like, could they create another Dyson sphere around the original one to capture all that leaked energy? And so you have like consecutive shells here, which would capture all that leaked energy, so you like minimize what's leaving.
Right. This is something, I don't know if it's in fiction or what, but there's this concept called like a matryoshka brain people have talked about, where you have a bunch of different layers. So like your inner one captures the energy straight off the star and it does some sort of high energy computation task or something, and then the energy goes down to the next level in temperature, does something, and then keeps going. But honestly, that's just like not very useful. You don't really need to have different energy levels for computational processes like that. Um, and like uh,
That's
your energy is generally eventually going to escape. You can't just hold it all in. So you use it for what you can. You get some waste heat, just kind of inevitable.
Okay. So another question here from the chat. How large did Dyson figure these rigid structures could be? And how large do you think they could be?
Yeah, that's a good question. I think in that Dyson paper I was talking about with the large structures, he said something like 1,000 kilometers in size. I have not done calculations of that type to see what I think would be reasonable. It's just not something I've worked on, but that was what Dyson thought.
Okay. And we have these different levels of civilization, like civilization 1, 2, 3. So, question: how soon until we are a Type 1 civilization, and what can we personally do to make that happen sooner? That was kind of a joke.
Yeah. I don't know. As far as we don't know of anyone who has done it before, so tough to say. Ask some engineers who are working on energy stuff. They might know better than me.
Fair enough. Are there any kind of stars which might be optimized? Like, would a type star be better because it generates a lot more energy? Would an M-type star be better because it doesn't have it so much in the UV? It's at longer wavelengths. Might it be easier to capture the longer wavelength energy than short wavelength energy?
Yeah, I think there's kind of a trade-off there to think about because higher mass stars are going to give off more energy, but they also don't live as long. So if you want a really long-lived civilization, you're going to want to go with a lower mass star that will keep burning for a long time. So depends if you want lots of energy right now or if you want your energy to last a long time.
Okay. All right, and one more. How far does a swarm need to be from the sun? Could we build prototypes that were at a distance around Earth's orbit like modern satellites?
Um, yeah, a lot of times when people talk about these, they imagine them being around the distance of Earth. Might just be biased because that's where we're at, but that's where it's imagined a lot. Especially if you want these objects to be habitable, if people are going to be living on them, it's got to be somewhere that liquid water can exist so that we can exist. People have also talked about deconstructing Mercury and making satellites at Mercury's orbit.
Just take apart
It's
the
a
entire
fun idea.
planet.
Just take apart Mercury.
We don't need what does Mercury contribute to the solar system? Not much, right? We don't have any planetary scientists on here, do we? All right. Well, thank you very much, Macy, for coming out and giving this talk. Really cool subject, and we really appreciate having you out here. Thank you.
Thanks.
All right. We are going to get started with our trivia. I have the trivia link, which I will post into the chat. So if you would like to play trivia, feel free to visit the link that's in the chat right now. Arvin will be on here pretty soon, I hope, to guide you through the questions. All right. All right, so I will hand this over to Arvin.
Cool. Thanks, Michael. Great talk, Macy. I like Mercury, so I don't think we should take it apart. But yeah, so for trivia, for those of you who have not been to our events before, welcome. I'll go through a quick description of how we do trivia because it would probably help you all to understand that. So what we do each month is we'll have a set of 15 themed questions. Tonight's theme is temperature. And I'll go through each of these questions here, and you guys all have the trivia link, which Michael posted in the YouTube chat, I think, and which also is on the slide here. And just go through those, answer them as best as you can. And by the end, whoever has the highest score out of 15 points will be selected to win some prizes that we have. You're also going to be asked to give a team name for your trivia. So in the case of a tie, so if two teams, for example, have 13 out of 15 correct, I will choose the team with the most creative astronomy themed name as the winner for the tiebreaker there. So if you think you're doing well, try to get creative and come up with something fun. Here are some of the prizes we have. We have Astronomy on Tap koozies, magnets, bottle openers, and also some masks that were actually sewn by Macy, who just gave that talk. So thank you, Macy, for getting us those masks. Okay, so we'll start off with a quick example question. This one here is Phobos. So I should have told you how this trivia works. What I'm going to do is I'm going to give you an object, and there's going to be some multiple choice, and you have to choose which of the multiple choice answers matches the temperature of the object that is in the question. So for this one, if I tell you Phobos, the correct answer would be Deimos, because these two are both moons of Mars, and they have roughly the same surface temperature because they're at the same distance from the sun. For all of the following questions, for the ones that are actually part of the trivia, the object that's up in the question is going to be something that is earthbound, so something that is on Earth that you might deal with in daily life, might not, but something that is on Earth and not in space. And everything that's in the multiple choice will be something in space. So the goal here is to match the earthbound object with something of a similar temperature that's out in space. So for number one, the question is the melting point of steel. And the options are the day side of Mercury, WASP 43b, Sirius, and a giant molecular cloud. For those who are not too familiar with astronomy terminology, the anything with a little b at the end here is usually an exoplanet. We give exoplanets names based on their host star. So the star here would be WASP 43, and B would be the first exoplanet in that system. Sirius is a star, it's the brightest star in the sky, and I think the other two are more or less self-explanatory. I'll also try to explain things as we go, but I won't explain everything because too many details might give away what the temperatures are. So number two is the center of the Earth, and the options are the surface of the sun, 51 Peg B, so again, this is an exoplanet, Enceladus, and Venus. And for things like Venus or Mars or the moon, I'm always referring to just the average temperature of it, not the peak or the low or something, unless I specify the maximum temperature or something like that. Number 3, the freezing point of CO2 or dry ice. I realize the top right there might actually be hidden by my video. Michael, let me know if that's wrong, but the question here is
You're
the
good.
freezing
You're
point.
good.
Okay, cool. The freezing point of CO2. And the options are the cosmic microwave background radiation, the surface of a white dwarf star, Kepler-16b, or Mars. Number 4, the state college temperature range. So this is the difference between the minimum and maximum record temperatures in State College, Pennsylvania, where we are located. The options are the cold neutral medium, the heliopause, a quasar jet, and Proxima Centauri. Number 5, the boiling point of water. The options here are TRAPPIST-1b, Saturn, a typical T Tauri star, or the day side of Mercury. Number 6, the temperature of a pizza oven, a photodissociation region. A photodissociation region is the region of gas surrounding a bright object that's emitting a lot of ionizing radiation. A typical M dwarf or Pi Mensae. And Pi Mensae is also an exoplanet. It just happens to be the second exoplanet in its system, so it has C instead of B for the terminology. And the last option is a supernova. Number 7, the best temperature to brew beer. And this image here is of our favorite Happy Valley Brewery, where we used to have our in-person events a year ago. The options are the surface of a white dwarf, Venus, Neptune, and TRAPPIST-1d. Number 8, the average global temperature change since the Industrial Revolution, so global warming. The options are the cold neutral medium. That's part of the interstellar medium, the space between stars. It's just one type of the gas there. Charon, the cosmic microwave background, and the ionization temperature of hydrogen. Number 9, the hottest part of a lightning bolt. I didn't really know how to explain this in short, but it's pretty much at the center of a lightning bolt. What is the temperature? And the options are WR25. WR is a Wolf-Rayet star. It's a certain type of star. The surface of the sun, TOI 700d, and Rigel. Number 10, the lowest temperature recorded in Antarctica. The options are Mars, Ganymede, a typical M dwarf star, or the night side of Mercury. Number 11, the inside of a volcano, a supernova, 51 Peg B, Aldebaran, or Proxima Centauri. Number 12, the summit of Mount Everest. Is it the moon, Titan, the cold neutral medium, or a typical T Tauri star? Number 13, an arc welding torch. And I'm not talking about the handle of the torch, I'm talking about the actual flame here. Is it TRAPPIST-1c, Polaris, a typical M dwarf, or a photodissociation region? Number 14, hydrothermal vents. Is it the star RR Lyrae, Venus, Jupiter, or K222b? And last but not least, the inside of a hot pocket. TOI 1231b, a quasar jet, Pluto, and the day side of Mercury. And I'm asking here about the temperature that you're supposed to heat the inside of a hot pocket to, not the extreme low or extreme high that you inevitably get. So I'm going to go through all of these again real quick. And you have until the end of Astronomy in the News, which is the next segment right after this, to get your answers in. So please make sure you do have them in before the end of that, because that's when I'm going to start grading and figuring out the winning team. 2. And also for these, I know I said they may be things that you encounter in your daily life, but I know almost none of them are, because the temperature ranges that we deal with on a day-to-day basis are very narrow, and things in space are not. They have very cold and very hot extremes. So I tried to pick out a lot of examples of things on Earth that actually match those extremes, so that we weren't saying the same object in space as the matching example for every single one of these. Yeah. 6. Also, if any of these were confusing to you and you would like a bit more explanation, I can try to do that. So maybe put a question in the chat, but again, I'm not going to say too much because I don't want to give away what source of temperatures all of these objects have.
Well, I got a question. When you talk about brewing beer, I mean, you got the temperature that you pitch the yeast at, and you got the temperature that you leave the beer to just brew. I mean, those are two very different temperatures, Arvin. Which one are we talking about here?
Michael, how different are those temperatures in astronomical contexts?
Different.
All
right, continue.
We're talking about the temperature that you're actually brewing it at. But yeah, Michael, please let me know if there are questions in the chat because I'm not looking there. Okay, and like I said, please try to submit before the end of Astronomy in the News. Make sure you have some creative names.
All right, so I'm going to hand this over to Brianna, who's going to give us a talk about astronomy in the news.
It wouldn't let me unmute when I had already started sharing my screen for some reason. Anyway, welcome to another month of Astronomy in the News. Macy got me all wanting to talk about aliens. I will be talking a lot about Mars, but not about aliens on Mars, so don't hold your breath for that. You may have heard on Thursday that NASA successfully landed the Perseverance rover on Mars. Very exciting time. And you can see a JPL engineer here looking in anticipation of a successful landing. This is a picture of the Perseverance rover. You can see it's quite large. On Earth, it's over 2,000 pounds. On Mars, it's less than half of that, but still quite large, about 10 feet long and 7 feet tall. You can see a person in the background to give you a general scale. Perseverance has a few general science goals. They are hoping to use it to search for biosignatures from ancient microbial life on Mars. So maybe some like ancient aliens a little bit. Not really though. Also characterize Mars's climate and geology and collect samples of rock and soil. They're going to store the samples in the rover and then hopefully find a way to return it to Earth for analysis at a later time, which will give us a really exciting opportunity to analyze things using instrumentation that is too big or too complicated to get on Mars in a rover. As you can see, everyone was celebrating like crazy once the landing was successful. Such a big thing is difficult to land on Mars, especially when it has so many moving parts and complicated components. This is a scheme of how they land it. Some of you may have actually watched the landing live. If you didn't, it's on YouTube, you can go watch it anytime. But basically, there are a lot of different things going on, and it has to be fully automated. People call it the 7 minutes of terror because there's a lag between Earth and Mars in terms of communicating with the rover. So the people at JPL can't be controlling the rover as it's descending onto Mars. And so they just have to hope that the parachute deploys properly, the heat shields come off properly, and it can descend gently. And then actually a big sky crane comes out and like gently lowers the rover onto the surface, which is an incredible feat of engineering. And everyone on the team is just holding their breath, hoping that it's happening properly. And they find out several minutes later. But everything went flawlessly. And there are a few other Mars things that I want to talk about. The first one being the HOPE orbiter. This is an orbiter from the United Arab Emirates Space Agency, and its main goal is to study the Martian atmosphere and weather, both long-term and short-term weather. And this is an image from the HOPE orbiter that came out just a few days ago. I think I forgot to mention, but Perseverance launched in July of 2020. So did the HOPE orbiter. And both of them just arrived this month in February. So really new and exciting things. This is a picture of the HOPE orbiter on Earth. And then China also had a Mars project going right now. So the China National Space Administration launched Tianwen-1 in July as well. And this consists of an orbiter, a lander, and a rover. And it made it to Mars successfully. It's currently in orbit. And then in about May or June, they're going to deploy everything that's going to land on the surface of Mars. So we'll have to just stay tuned for that and hope that everything goes well for them moving forward. But there's definitely going to be a lot of good science from this mission as well. Tianwen-1 is China's first mission to a different planet. So they have a lot planned for it. It's going to be studying the geology and structure of the Martian surface, the distribution of water ice, rock composition, and they also plan to collect samples just like Perseverance is. And they're also going to study the Martian atmosphere and weather, as well as its magnetic field, among other things. There was just tons when I was reading up on this mission. So congratulations to the Perseverance, HOPE, and Tianwen-1 teams. All of them had successful launches back in July, and now all of them have made it safely to Mars. And I think that we're going to see a lot of really exciting science coming from all three of these missions in the coming years.
All right, thank you, Brianna. So we have our next speaker coming up. If you haven't already, please do submit your trivia questions. We'll grade them during the break. And we'll get to the answers of the winner after our next talk, which is going to be by Alex Bells, another astronomy graduate student at Penn State. And he is going to be telling us all about dust. So go ahead, Alex. Oh, also, I finally remembered, if you have questions for the speaker, put them in the chat. Usually you have to type that in the chat because I always forget. But if you have questions for Alex, please type them in the chat. Okay, go ahead, Alex.
All right, can you see my slides? Cool. So hi, my name is Alex Bells. I'm a third-year grad student at Penn State. And first off, I also want to say thanks to the Astro on Tap organizers for inviting me to give this talk today. The title of my talk is How Dust Distorts Our View of the Universe. So on this title slide, I have a picture of one of my favorite galaxies. This is M104, also known as the Sombrero Galaxy. The reason it is called the Sombrero Galaxy is because it kind of looks like a hat. So the rim of the hat is defined by the dust. That's that dark streak through the image that we see. Dust is a rather small amount of the material that is in galaxies, but it has a very large and oversized effect in astronomy and astrophysics. So I wanted to focus here on some of the observational effects of dust. So first, I need to talk about and explain what is dust. So astrophysical dust is not the dust that you find in your house. It is not the combination of skin and hair cells that you find underneath your couch when you clean it over the weekend. What it actually is particulate matter that is made up of carbon and silicates. So on the right of this slide here is what dust looks like. There are these grains that are 10 microns in size. And a micron is a millionth of a meter. So comparing these grains of dust that are in the universe and the galaxy to stuff that we know about on Earth, they're very similar to smoke particles. So to begin my talk, I'm going to go over some pictures from the Astronomy Picture of the Day archive that show dust in various different forms. So the first picture is the Milky Way. So if you're lucky enough to get outside on nice clear night, if you try to do it soon, it'll be very cold. You might be treated to this view. The dark lanes that are shown here are due to dust in the plane of the Milky Way galaxy, where the bulk of the star formation occurs. So this dust lies between the stars in what astronomers call the interstellar medium. So when it is very dark due to the presence of dust, that doesn't mean that there are not stars behind it. It means that the dust is blocking the light from background objects. It's not something that we can easily get around. Some astronomers might wish that they had a cosmic vacuum cleaner so that they could get rid of the dust so that it is easier to observe the stars in the Milky Way. But sadly, this is just something that we all have to deal with. If you stay outside all night and wait until sunrise, you might see something like this. So this is an image from Chile just before sunrise. And the arrow on the slide here is pointing at something called the zodiacal light. What the zodiacal light is light from the sun scattering off dust in the solar system. So the dust is in the plane of the solar system, and due to collisions of asteroids or the tails of comets evaporating, this dust lines the plane, and just before sunrise or sunset, you might see this characteristic line extending from your horizon up to the Milky Way. A little known astronomer called Brian May studied the zodiacal light and the zodiacal dust. For those of you that don't know, Brian May was in a very famous band called Queen. He was a graduate student at the Imperial College London in the 70s, decided to take a break from his studies to be a rock star, and then eventually in the late 2000s went back to school and got his PhD. And this paper shown here is from one of the papers that he published in graduate school talking about the zodiacal light. So last image I have here at the beginning is of objects called Barnard 68, which appears to be a void in space. It's not actually a void, but it is a dark molecular cloud. This is a cloud of gas and dust that is very dense and has a lot of dust, and it is the site of star formation. So within that cloud, a young star is being born. So as I just went through those three examples, dust has very interesting effects on the observations that astronomers are able to do. In addition to the effects on these observations, dust plays a very important role in the physics that governs the universe. During this talk, I'm not going to talk about the physical processes related to dust, such as its role in star formation and how dust forms in the outer envelopes of evolved stars. But if anyone has any questions about those, I'm happy to answer that at the end. What I'm going to focus on here are these three main takeaways: that dust extinguishes light from objects and can hide the objects from view. The effects of dust have a wavelength dependence, which leads to the effects of dust being referred to as reddening. And lastly, dust reprocesses the light that it absorbs and emits it in the far infrared. So now I'm going to go through and talk about each of those three different ways that dust affects our observations. First one is that dust can hide or obscure objects. So this is another image from the Astronomy Picture of the Day archive showing a cloud of dust in space that makes it very difficult to observe things in the background. So why is this important? Well, when dust diminishes the brightness of objects, it makes it difficult to know what is the true intrinsic properties of the objects that you're studying. So if you're studying specific stars that are dimmed by the presence of dust, that makes it difficult to say, are these stars dim because they are far away, or is it because they are behind dust? In astronomy, measuring distances to objects is very difficult. So these effects of dust make that, even though you need to have a good understanding of the effects of dust, along the line of sight to your object of interest in order to be able to do the astrophysics that you're interested in. And one of the earliest papers that I could find talking about the effects of dust on observations was from 1930. So this is a very old paper by someone named Trumpler. What Trumpler did is measured star clusters in the Milky Way. And what he did is he measured the distance to them in two different ways. The first way is what he called the diameter distance. So what he did is assumed that star clusters were one size, and as they got farther and farther away in the Milky Way, they appeared smaller and smaller. It's a well-known perspective effect, and by making this assumption that all star clusters are the same size, he can estimate the distance to them. So he compared that distance to the light's distance. So assuming that you understand what the intrinsic brightnesses of these star clusters are, based on the effects of distance with light, so something farther away appears dimmer than something close by, you're able to estimate what the light's distance is, and that's what's plotted on the x-axis. So you would assume that these two distances would agree. Okay, the distance of the object should not matter based on the method you use to measure it. But what is found is that the light distance always gave a larger distance as these star clusters got farther and farther away. So this was one of the first times that astronomers were able to quantify how dust affects observations, and that things that are farther away have more dust between them and us, which makes them appear dimmer. So we tend to think that they are farther away. Another example about how dust can make objects appear dimmer is something that Macy talked about earlier today. So there is the Where's the Flux star that had a very peculiar light curve. And as Macy said, the news media kind of went wild and assumed, or went off this kind of offhanded comment that it was an alien megastructure. So there were many articles back when this first came out in 2015 trying to basically say that we found aliens. And as Macy explained, it's not quite true. So this plot here shows what the early light curve of this object is. So the Kepler Space Telescope observed this object very frequently and plotted its brightness as a function of time. And these weird dips at the end of this light curve here were hard to explain by conventional stellar astrophysics or the orbits of planets. Hence why some people thought that a partially built Dyson sphere was responsible, but further observations and invoking Occam's razor, the more likely scenario is that comets or asteroids created a lot of dust in the plane of the planet, and as they orbit around the star, the dust blocks the light and makes it appear dimmer, giving you those weird dips in the light curve. And since the dust is not necessarily smoothly situated in the plane, that's how you can explain that there's these non-periodic dips. Another way that dust can infuriate some astronomers is if they are interested in other galaxies like I am. So to observe galaxies outside of the Milky Way, you have to look through the Milky Way in order to see them. This creates this so-called zone of avoidance, which is basically just a fancy word for the plane of the Milky Way. So the dust in the plane of the Milky Way and the stellar emission from the stars in the galaxy obscure approximately 20% of the sky, meaning that it's very difficult to find galaxies that are hidden by the dust in the galaxy. So this is very important when you're doing studies of the positions of galaxies like they do in cosmology. This is a fairly famous picture from the Sloan Digital Sky Survey plotting the positions of all galaxies relatively nearby, going out to far distances. And as you can see, we don't get a full coverage of the sky, partially due to this zone of avoidance, making it very hard to find galaxies that are hidden by the plane of the Milky Way. In fact, one of the biggest mysteries that exists because of the zone of avoidance is something called the Great Attractor. The Great Attractor is the name of a large, massive object hidden behind the Milky Way. So this object is more massive than a single galaxy. It is thought to be a cluster of galaxies, but because it is located behind the plane of the Milky Way, the dust makes it very difficult to observe. But by indirectly observing the motions of other nearby galaxies, we're able to deduce how massive it is, and that something is there. So the next main takeaway about how dust affects our observations I want to talk about is how dust changes the color of objects. So this is a picture of the sunset, and as most of you know, the sunset appears red rather than the normal color that the sun is if you look at it during the day. The reason for this is very similar to the effects of dust in the universe. So the light from the sun at sunrise or sunset has to travel through more of the atmosphere in order to reach us. And as the light has to travel through the atmosphere, it can encounter particles and matter that will scatter it out of our line of sight. And just like the effects of dust, there's a wavelength dependence where blue light is more likely to be scattered than the red light, hence why the sunset appears red. In a graphical form, it is something like here on the left. So if we have a star that is intrinsically blue, it emits mostly blue light, but also some red light. As that light travels towards us, observing here on Earth, it might encounter a screen of dust between us and the star. And as the light travels through the dust, the red and the blue light will be affected differently. The blue light will be scattered and absorbed more by the dust than the red light. So what happens is once it emerges from this screen of dust, the red light has an easier time making it through. So this intrinsically blue object can appear redder because of the effects of dust, hence why this effect is typically called reddening. When astronomers are looking at other galaxies that contain dust in them, the effect is a bit more complicated. The stars and the dust are intermixed. So on the right here, it is not a simple scenario where the light from the star, light from each star passes through the same amount of dust. It is different based on what part of the plot you're looking at. So the effects of dust in other galaxies is much more complicated than looking at stars in the Milky Way. And studying the effects of dust in other galaxies is an object of research. So sticking in the Milky Way and talking about the wavelength-dependent effects of dust, previously I showed you Barnard 68, the molecular cloud. And if we start on the top left of this picture and then go through it counterclockwise, we go from images in the optical, so what your eye would see if you were able to look through a telescope and look at it, progressively looking at redder and redder light until it gets into the infrared. So as we go from the top left image to the top right image, it becomes a little less dark at this molecular cloud. And as you get to the infrared wavelengths on the bottom panel, you can start to see through the molecular cloud. So what this means is that at infrared wavelengths, objects can become transparent, even though in the optical visible part of the spectrum, they look opaque. An example of this, looking outside the galaxy, is IC 342, which is nicknamed Hidden Galaxy. So this is the third largest spiral galaxy nearby after Andromeda and the Triangulum, but it is hidden behind the Milky Way. So the optical image on the left is not quite as pretty as an image of Andromeda. However, once you go to infrared wavelengths where it is easier to see through the Milky Way galaxy, you see a much more defined spiral pattern of this galaxy. If you go to the ultraviolet part of the spectrum, it becomes even harder to see what the object is. So this is an example of Swift Ultraviolet Optical Telescope data of IC 342. And looking at this image, it's really hard to tell that there's a spiral galaxy here due to the heavy effects of dust. Shown graphically, this is what the dust extinction law looks like. So the human eye can see between 0.35 microns to 0.75 microns, and the dust extinction effects in that range are well understood and agree when you look at different galaxies and different sight lines within the Milky Way. However, once you get shortward of that, so looking at bluer wavelengths in the ultraviolet, they diverge. Different sight lines in the Milky Way affect ultraviolet light differently based on the composition and the amount of dust, and trying to understand how the ultraviolet extinction law works is a topic of interest. So the last way that dust affects our observations is that it emits at longer wavelengths. So this is a picture of Andromeda. In the visible, you see what you might see looking through a telescope, but in the infrared, you see this bright emission that lines up with the dust in the galaxy. So the way that this works is that dust absorbs the blue light, and then it'll eventually re-emit it at infrared wavelengths. This is a process called thermal emission, where the temperature of the dust is what sets the spectrum that we see. The dust emission is the dominant component in the infrared, looking at other galaxies. This sort of reprocessing of ultraviolet and optical light has this sort of an effect. So the spectrum of a mock galaxy that was simulated is shown in blue, and then applying the effects of dust, we get the extinction at the optical and ultraviolet, and then this large amount of emission in the infrared. Using the infrared emission of galaxies is something that astronomers use to find galaxies. So there is a class of objects called ultraluminous infrared galaxies. They get this really great acronym called ULIRGs. ULIRGs are very vigorously star-forming galaxies that have a large amount of infrared radiation. The classic example is ARP-22, which are two spiral galaxies that are merging. The last effect I want to talk about with dust emission is in cosmology, they look at the cosmic microwave background. And microwave is part of the infrared spectrum, and dust emits in the microwave, which makes the job of understanding the CMB spectrum and the small differences on very small spatial scales very hard. So this is what the typical raw data might look like, where you see the dust emission from the plane of the Milky Way. That then gets cleaned out. The astronomers who study the CMB do a great job of correcting for this foreground contamination in order to measure the CMB spectrum, which is almost a perfect black body at 2.73 Kelvin, but has these very small fluctuations at 10 to the minus 5 that are shown on the left. So the main takeaways I hope everyone got from my talk is that dust reduces the brightness of objects and can make them appear dimmer. However, this effect is also a function of wavelength, where blue light is more easily affected by dust than red light. And lastly, the light that the dust absorbs then gets re-emitted in the far infrared and can be used to find galaxies. So thanks for listening to my talk.
All right, thank you, Alex. So again, if you do have any questions for our speaker, feel free to type them into the chat and we can ask them while he is still here. So one question I have is, we talk a lot about dust and how it's everywhere in the galaxy. Do we think that dust is the same in our galaxy versus dust in other galaxies, or even dust in certain parts of our galaxies versus other parts? Do we think it's all made of the same stuff?
Right, so that's a good question. So the composition of dust directly affects it, how it absorbs light. So the different size of the dust particles will affect what sort of light it is better at absorbing. So sight lines in the Milky Way galaxy towards more dense regions like molecular clouds have a flatter extinction law, meaning that there's less dependence on wavelength compared to other regions where the wavelength dependence is more steep, and that is related to the composition of dust.
Okay. Is there a way to know if the dust that we're seeing, like if we look at some other galaxy, do we know if the dust we're seeing is coming from our Milky Way, our galaxy, versus coming from the other galaxies? Is there a way we can distinguish between the two?
So the dust in the Milky Way has been studied a lot, and the way that people have mapped it out is by looking at the emission from dust. And these maps of emission have been measured and then used to create a sort of how-to to correct for dust along that sight line. So if you're measuring, if you're interested in the emission from a certain galaxy, astronomers have already measured the amount of dust emission from the Milky Way along that direction, which allows you to separate the contribution from the dust of the Milky Way affecting your data from the dust internal to the galaxy and how that affects your data. To answer your question?
I think so. Yeah. Would space dust still make you sneeze? Do aliens have space dust allergies?
That is a great question. I hope not, because that dust is not a fun allergy to have. I can tell you that.
All right. And you mentioned earlier in the talk to ask you how dust is formed in stars. So, Alex, how is dust formed?
Yeah. So, as I mentioned in the beginning, dust is made from carbon and silicates, and these are molecules. So, in order to form molecules, you need to have very certain conditions. So, the main theory of where dust forms are in the outer envelopes of stars. So, stars that are more evolved than our sun, typically on the red giant branch or the asymptotic giant branch, their outer envelopes are so far away from the center of the star that it is actually cool enough for molecules to form. So it is thought that these molecules form in the outer envelopes of these evolved stars that then lose that mass, and it gets added to the ISM, the interstellar medium, and makes our lives more difficult as astronomers.
Unless you're actually studying the dust, right? And then it's great.
Yes. Unless you're like me and you're interested, or Brian May and you're interested in the dust.
So I got to ask about Brian May. I know he came back and did his PhD. Was it on the dust as well? I
Yep.
can't remember what his thesis was on.
Yeah, it was on the zodiacal dust. So apparently in the 30 plus years from when he started graduate school in the early 70s and when he got his PhD in the late 2000s, the field of the zodiacal dust had not moved very fast. So he was able to finish his PhD quicker than he imagined because, the results he had, 40 years ago were still good.
Okay. It's a pretty good career to come back and do a PhD after coming back from Queen.
Yeah. Rock star to get your PhD.
Yeah. That's the typical career path of a graduate student. So are there different there's different types of galaxies. You got spiral galaxies that you showed us that have this beautiful dust. You've got elliptical galaxies, which are a bit different than spirals. You've got irregular galaxies. Is there any difference in kind of the dust distribution between the different kinds of galaxies that we have in our universe?
That's a good question. I don't know if there are broad differences based on the category of galaxy. So say whether or not, in general, elliptical galaxies have very different dust content than spiral galaxies. But, even going from a galaxy like the Milky Way to the Magellanic Cloud, so the two of the largest satellites of the Milky Way galaxy, they have very different dust features, especially in the ultraviolet.
Okay. And then one last question. We're looking at those really dark patches in the sky where look at optical and it's just completely black. You can't see anything through it. Do we have an idea for how much like physical dust there is in between us and those stars? Like how much either in mass or how much in like density? Like how much actual dust is required to block out our view of stars?
Right. The answer is it's a lot, but I don't have a number or a quantification of that offhand. So I apologize.
Okay, that's okay. All right. Well, thank you very much, Alex, for coming out and giving this talk. Really appreciate it. Thanks.
Yeah, thanks for having me.
All right. So now we want to come back and get our trivia answers from Arvin and announce our winner.
Cool. Again, thank you, Alex, for that talk. Really cool stuff. But it's time to figure out what the answers were for trivia. So I think I'm sharing the answers right now. Might be the questions, but we'll figure that out soon enough. I'm just going to go through and show what each of the answers were, and then at the end I will let you all know who the winner was. So for our prizes, again, this is what's at stake. First question, the melting point of steel. This is actually very similar to the temperature, the equilibrium surface temperature of the exoplanet WASP-43b. It's about 1700 Kelvin. The day side of Mercury is much cooler than that, actually. Sirius is a star, which is thousands of Kelvin, and a giant molecular cloud is fairly cool. The center of the Earth is actually very similar in temperature to the surface of the sun. They're within a few hundred Kelvin of each other. 51 Peg B is an exoplanet that's much cooler than that. Enceladus is a moon of Saturn that's only in the tens of Kelvin. And then Venus, again, is not quite 1,000. The freezing point is CO2, or dry ice. This is very similar to the surface temperature of Mars. Mars actually has some CO2 ice caps. Number 4, the range of temperatures in State College. So I could be wrong about this, but when I looked it up, it looks like the record low in State College is -20 Fahrenheit, and the record high is about 120 or 102. And that range corresponds roughly to the temperature of the cold neutral medium in the ISM. That's about 80 Kelvin. The boiling point of water, this is 100 degrees Celsius or 373 Kelvin, and that's very similar to TRAPPIST-1b. So TRAPPIST-1 is actually it's a star with 7 exoplanets orbiting it. And TRAPPIST-1b is just interior to the habitable zone, so water would boil on its surface and wouldn't be at a temperature that is hospitable to life. Temperature of a pizza oven. The correct answer is a photodissociation region. So if you wanted to make a pizza out in space, you should put it here, although the pressure and lack of any air and density would probably make it not work. A lot of people answered pi Mensae C here. This exoplanet is actually a little bit too hot by a few hundred Kelvin, so you'd end up burning your pizza there. Number 7, the best temperature to brew beer. Despite Michael's complaints, the only correct answer is TRAPPIST-1d. Again, this is another exoplanet in that TRAPPIST-1 system that has a surface temperature that's very close to the temperature here on Earth, because the correct answer for the best temperature to brew beer is just room temperature. So the surface of a white dwarf is tens of thousands of Kelvin. Venus is several hundred Kelvin hotter than room temperature, and Neptune is much colder. So none of those, I think, would work in any part of the process of brewing beer. Number 8, the average global temperature change since the Industrial Revolution. We've seen a rise of about 1 degree Celsius or 1 Kelvin. The only thing close to that here is the cosmic microwave background, which is about 3 Kelvin. Number 9, the hottest part of a lightning bolt. It's about 50,000 Kelvin, which is the temperature of Wolf-Rayet 25. So Rigel is a very hot, very bright star, but it's only, I guess, 10,000 Kelvin. Still really hot, but that might be closer to the temperature in the air surrounding the lightning that's getting heated up there. Number 10, the lowest temperature recorded in Antarctica. This is also about the surface temperature of Mars. Number 11, the inside of a volcano. Volcanoes aren't quite as hot as stars, so it won't be supernova, it won't be Aldebaran or Proxima Cen, but 51 Pegasi b, which was the first exoplanet detected around a sun-like star, it won the Nobel Prize a few years ago, is about 1300 Kelvin, which is close to the inside of a volcano. Number 12, the summit of Mount Everest is very close to the surface temperature of the moon, actually. So if you want to know what it's like to be on the moon without actually going to the moon, all you need to do is climb Mount Everest. It's a lot easier. Number 13, an arc welding torch. These things actually get really hot. It depends on what the gas is that you're using, but some of them are close to the 3,500 Kelvin of a typical M dwarf. Others are a little bit cooler at 2,500 Kelvin, but that's still not close to the temperatures of these other options here. Number 14, hydrothermal vents. These get up to about 700 Kelvin, 750, which is very similar to the temperature of Venus. So our Lyra stars and KT22b are much hotter, and water actually can't exist in a liquid phase much higher than 750 or 800 Kelvin. So these would not be viable answers. Number 15, last but not least, the inside of a hot pocket. You guys should all know this. It's 165 Fahrenheit, the safe temperature for cooking food. And if anybody attended the exoplanet seminar today at Penn State, you would know that TOI 1231b is also roughly that temperature. So that's the correct answer. The winner tonight, it was actually a tie. There were 2 teams that got 10 out of 15 correct. But I thought this one was a little bit more creative. The astronomy themed Pokemon Swarm and Sphere. I guess it was a take on Dyson Swarm and Sphere. So if that was you, I will be contacting you later this week to talk to you about getting you your prizes. Congratulations, and thank you to everybody for playing.
All right, thank you, Arvin. Thank you again to all of our speakers and to all of our co-hosts, Arvin, Brianna, Jacob. We do have another event coming up for you in 1 month. March 22nd, we're going to be talking about dark energy and dark matter. So go ahead and block that day off of your calendar. March 22nd, 7 p.m. See you back here at Astronomy on Tap. Jacob, I believe you have a message you want to give.
Yeah, I have a quick shout out to, I think, a record breaker. We have what I think is, and what I assume is, our youngest viewer Maya Anthony at 2 days and like 6.5 hours old. So that's going to be a tough record to beat. Good work, Maya.
Awesome. I hope you enjoyed it, Maya. I hope you had a good time at Astronomy on Tap. Hopefully you didn't drink the beer, but we'll allow that. All right. Well, thank you again, everyone, for coming out. We're on Facebook, we're on Twitter, we're on YouTube. Follow us, like us, do all that good stuff, and we hope to see you back again in March. Thanks.